Hi friends, in this video we will be talking about Dijkstra single source shortest path algorithm. So given a graph and given a source vertex of the graph, we have to find the shortest path from the source to all other vertices in the given graph. So Dijkstra's algorithm will be finding a single source shortest path. So the algorithm of Dijkstra is, let us see, the first step is to create an empty set, which is we will be calling it as SPT set, that is shortest path tree set. The set will be containing all the vertices which are included in the shortest path. So initially that set will be empty, that is we have not found the shortest path vertices. Okay, so next second step is assigning values to the vertices, distance values to the vertices in the input graph. So we'll be assigning a 0 value to the source, and remaining all vertices will be having a infinite value. So we'll be initializing all the vertices distance values as infinite except the source vertices, which is given as 0. And now the next step is we'll be including all the vertices in repeated fashion. So we'll be performing these steps, A, B, C steps, until all the vertices in the given graph are included into our shortest path tree set, that is SPT set. So what we'll be doing is we'll be picking a vertex u which is not present in SPT set and which has a minimum distance value, and we'll be including that vertices into the SPT set. And after including the value of that vertices into the SPT set, so we have to update the distance values of adjacent vertices of u. So if we want to update the distance values of adjacent vertices, so we have to find all the adjacent vertices, and we'll be taking the value of distance value of u, and we'll be taking the weight wedge of u to v vertices, and we'll be adding that, and we will be updating distance value of v if it is less than the already present value. So this is how these steps will be continued until all the vertices of the graph are included into the SPT set. So let us consider an example. So this is the given graph and with the corresponding edge weights, and we'll be considering this as the source vertex, 0 as the source vertex. Okay, so initially SPT set, that is shortest path tree set, will be empty. Okay, and remaining we'll be assigning 0 distance value to the source vertex, and remaining all the vertices are assigned infinity. Okay, distance values of all other vertices are assigned as infinity. Okay, so this is what. Now we'll be considering 0 as our vertex u, and we will be finding all the adjacent vertices. So adjacent vertices to 0 are 1 and 7. So we have to update the vertices distance values of these vertices. So the distance values are, so the 0 plus 4, 0 plus 4, it will be 4, 0 plus 8, it will be 8. So 4 is less than infinity, so updated. 8 is less than infinity, it is updated. The next we'll be picking 1 with shortest distance value. So now the adjacent vertices to 1 are 2 and 7. So if we consider 1 to 2, the path weight is 8. So 4 plus 8, it is 12. 12 is less than infinity, it is updated. And when you consider the adjacent vertices 7, and weight is 1 to 7 is 11. So 4 plus 11 is 15, but we already reached 7 with the cost of 8. So 11 plus 4 15 is greater than 8, so it will not be updated. So next we will be considering the vertices 7 with shortest value, and the adjacent vertices to 7 are 8 and 6. So we will be updating the values here. So 8 plus 7 is 15. So the vertex distance value of 8 is 15. 8 plus 1 is 9. The distance value of vertex 6 is 9, which are less than infinity, so updated. So now these 3 are included in the SPT set, and now these 3 have to be checked. So again we will be considering 6. So when you consider 6, the adjacent vertices of 6 are 8, 5, 8 and 5. So if we go for 9 plus 6, it is 15. So you can consider this, we are making the shortest path from here, it is 15. Then Next one is 6 to 5, 6 to 5. So 9 plus 2 is 11. So we have updated it to 11. So this is what when we are considering 6. So now similar fashion, if you repeat all these steps, so let us this is what we have got here. Next we will be considering, so remaining vertices, so 6 is included into the SPT set. So not included sets are 2, 8 and 5. So least value is 5. So if we consider 5, we will be having the adjacent vertices 2, 3 and 4. So we are computing the values. So 5 to 2, 5 to 2 we will be getting 15. So 2 already reached with 12, so no update. Then 5 to 3, so 5 to 3 it is 25. So 25 is less than infinity, it is updated. Then 5 to 4, so we will be getting 21. 21 is less than infinity, so it is updated. So now we will be getting this graph. So and 5 is included into our SPT set. So not included vertices are 2, 3 and 4. So now we are considering the least value is value vertices distance value 2. So we have two adjacent vertices 2 to 8, 2 to 3 and 2 to 5. So corresponding values distance values constructed. So if you consider 2 to 8, we are getting it 14. So here already 8 was reached with 15. So 14 is less than 15. So we will be updating the path as 2 to 8 with 14. So this path will be removed. Okay, so we will be updating this. Next one is next adjacent is 2 to 3. So we are getting 19. So 19 is less than 25. So we are updating this path also. So we will be removing this path and we will be updating this path with 19. And next one is 2 to 5. So 2 to 5. So 2 to 5 is 19. So we already reached 5 with 11. So 19 is greater than 11. So it is not updated. So now 2 is included into the SPT set. So vertices not included are 3 and 4. Okay, so when we come to 3, adjacent vertices to 3 are 5 and 4. So if we go from 3 to 5, the value will be 33, which is greater, so not updated. 3 to 4, the value is 28, which is greater, so not updated. So now 3 is included into set. Now coming to 4. So you can see there are no adjacent vertices which are not included in SPT set. So this is what at the final we will be getting the shortest path graph. So you can see that 4 can be reached through this way with cost distance of 21. 8 can be reached with cost distance of 14. 3 can be reached with cost distance of 19. Okay, so from source you can reach every vertices in the shortest path. So this is what Dijkstra's single source shortest path algorithm. And remember that this algorithm will not work if there are negative edge weights. That is, if any edge contains negative weight, Dijkstra's algorithm will not work. So if there are negative edge weights, we have to consider Bellman-Ford algorithm. Hope you understood. Thank you.